We've already seen how base-2 allows us to deal with keeping up with who will win in NIM. Now let's look at another problem we can solve using different bases, which is a problem I love called the counterfeit coin problem. We have some number of coins. Let's start out saying it's 7 coins. And we have a balanced scale. So I don't get any numbers out of this scale. All I get is a comparison that will tell me whether one side is heavier or the other. I know that one coin is lighter than the others. And in addition to that, what I want to know is how many times will I need to put coins on the scale to figure out which coin it is. And I'm going to claim that the answer is 2. And I don't want you to believe me. I want to give you a proof. I want to show that I want to claim you can do this in 2 ways. How am I going to do that? Well, I'm going to write out my 7. I'm going to have my 7 coins, and I'm going to first number them from 0 up to 6. So there are 7 coins here. I'm going to number them from 0 to 6. Are y'all with me so far? 0 to 6, I'm going to have, and now I'm going to write it in base-3. So 6 in base-3 I can write as 2, 0. That's 2 times 3 plus 0 times 1. 5 I can write as 1, 2, 1 times 3 plus 2 times 1. 4 I can write as 1, 1. 3 I can write as 1, 0. 2 I can write as 0, 2. 1 I can write as 0, 1. And 0 I can write as 0, 0. So now I've given each of my coins a label. And what I'm going to do is I'm going to take all the ones that start with 0 and all the ones that start with 1, and I'm going to I'm going to put one of these on one side and one of these on the other. So I'm going to call this left side of the balance, the 0 spot. I'm going to put this to be the 1 spot. And then if something isn't on the scale, I'm going to call it the 2 spot. So my first weighing is going to be 0, 0, 0, 1, 0, 2, or 0, 1, 2. And then I'm going to have 1, 0 base-3, 1, 1 base-3, and 1, 2 base-3, which will be the same thing as 3, 4, 5. And then off the scale in the 2 spot, I'll have my 2, 0 or my 6. Now, if the 0 spot's light, I know that it's one of these 3 coins. If the 1 spot's light, I know it's one of these 3 coins. And if the 2 spots, if neither one's light, then I know that it's in the 2 spot. So let's make that a little bit more concrete. Let's say that in this particular one, that the counterfeit coin was 5, which we labeled 1, 2. What's going to happen on this first weighing? Is the 0 spot or the 1 spot going to be light? The 1 spot, yep. So we do the first weighing, and the 1 spot is light. So that tells us that either 3, 4, or 5 is the light coin. So then we're going to do weigh number 2, and now we're going to totally forget about the first digit. We're going to go to the next digit, and so on the 0 spot we'll put 3, because now we're on the second step, and on the 1 spot we'll put 4, and in the 2 spot off of the thing we'll put 5. Now what's going to happen if 5 is the light one is that the balance will stay balanced. And so all I have to do is read the spots that I got, 1, 2, and that tells me which coin was light. So since I could encode every single coin so that it had 2 digits in base-3, that means I only need 2 ways. Does that make sense? And so when you do this for any number, all you have to look at is, basically how many symbols does the number have base-3. So if we look at how many symbols does the number have base-3, that's going to be equal to the number of ways that I need on this balanced scale to determine which coin is the counterfeit coin if I know that the coin is light. So for instance, let's say we have 117 counterfeit, or 117 coins, and we know that 1 is counterfeit. What we need to do to figure out how many ways we need is to convert 17 to base, or 117 to base 3. So converting 117 to base 3, we can use our algorithm. So 117, okay, 1 plus 1 plus 7 is 9. So I know it's evenly divisible by 3. I don't know what it is off the top of my head. It's 33 plus, it's 39 with a remainder of 0. And then I divide by 3. I get 13 with a remainder of 0, and then I divide by 3. I get 4 with a remainder of 1. Divide by 3, and I get 1 with a remainder of 1. I divide by 3, and I get 0 with a remainder of 1. And then I read up from the bottom. So 117 is equal to 11100 base 3. So how many times will I need to put coins on the balance to figure out which coin is the counterfeit one? 5. Because you have 1, 2, 3, 4, 5 symbols. This is a length 5 ternary string. So because there are 5 things here, you need 5 ways on the balance.